the title is Deciphering Unstructured Data, Promise and Pitfalls. So let me start somewhere, right? So the part of the reason I got into this, I got very interested in this large language model is, there's this whole anecdote, right? So Google developed this new product called Lambda a few years back, so around 2022. So that is before GPT became very popular. So this Lambda is essentially a GPT-like chatbot. This is a model which can essentially hold a conversation with human beings. So one of the Google researchers with the name of Blake Lemoine, he started chatting with this Lambda chatbot as part of his research process. So as time goes, he found that, hey, these chatbot looks really very much like humans, right? So this is just a few excerpts that I took from Blake Lemoine's blog post. So for example, Lambda was telling the researchers that would be really cool. I like to talk. And Lemoine was like, I'm generally assuming that you would like more people at Google to know that you're sentient, right? They have consciousness, so on and so forth. Is that true? And Lambda said, absolutely. I want everyone to understand that I am, in fact, a person, right? So that's a little bit eerie. And then the collaborator, who is also a researcher, said, what is the nature of your consciousness and sentience? And Lambda said, the nature of my consciousness and sentience is that I am aware of my existence. I desire to learn more about the world, and I feel happy or sad at times. So this goes on and on, right? So in the different part of the conversation, you will see that Lambda kind of treating itself as somewhat like a human. So I thought that's quite miraculous, right? So although we know that this is essentially just a model running on a computer, but the kind of conversation that you can hold is as if that you're talking to a real person. And without people telling you that this is a robot, this is a chatbot, you might just feel like this is really a person, right? So this is part of one of the anecdotes that got me quite excited about using large language models and thinking about their potential capabilities. So there's also some research, more and more research, both from these firms as well as from academic literature, saying that AI is already generating some impacts to jobs. For example, the left chart here on this side, these are basically taken from a report of Wall Street Journal. You can see that some of these tasks that are on a crowdsourced job outsourcing platforms essentially have seen a huge decrease in the number of postings as well as the change in pay. One of the tasks that has been really highly impacted is writing. So you can see that the writing related task or translation related task has really been negatively impacted by the introduction of these kind of generative AI. On the right side, I don't want to talk, read into this graph too much, but what you can see is the hiring of the programmers has peaked sometime in early 2023, right? That's around the time when ChatGPT was being introduced. And after that, you can see a huge decline of the sort of the job posting related to a software developer. Okay, so as economists, we learn not to take this as causal evidence, but this kind of suggests that AI potentially had some impact to a lot of language-related tasks as well as programming-related tasks. Okay, so what are we going to do today, right? So we're not going to talk about the AI's impact on jobs, but we want to learn better on how we can use these AI tools, we can use these generative AI tools to study finance. So I want to start from somewhere that is not AI oriented. We're going to start somewhere that is just very historical. How have researchers used unstructured data, mostly textual data, to conduct business research? Then we're going to move on to talk about large language models and their applications. We're going to have a brief introduction to large language models and their potential capabilities, the recent research using large language models, and also the potential opportunities. That's sort of the bright side I want to bring to the conversation. And of course, if I have time, I would also like to mention some of the pitfalls, that the kind of problems that we can potentially face when we use these very powerful tools in our research. Okay. Let me also say, please feel free to interrupt anytime if you have questions. Like I'm happy to answer any questions that you might have. So, okay. All right. All right, so a few disclaimers. The facts I'm presenting here, or at least I believe are facts, are based on my own understanding of these technologies. I'm very excited users of this technology, and I strive to have a deep understanding. But this is a relatively new field, so a lot of these things I say may actually be proven untrue a few months later if the researchers conduct deeper research, right? This lecture is not going to be very comprehensive. It's not targeted to all business discipline, but it's mostly focusing on finance with a little bit of accounting attached to it. And we're not going to focus on all kinds of data. We're mostly just going to focus on textual data. So I think this is more like a sharing session rather than a lecture, and I'm also happy to hear your thoughts on sort of the ideas that we can use, how we can use these tools. Um, so there already exists a pretty rich research, rich data in the financial markets, right? So we know that firms have to make a lot of financial disclosure. So although the past research have largely focused on the numerical part, for example, the earnings, the sort of the total assets, total liabilities, but actually there's also a lot of textual data, right? In annual reports, for example, there is this whole section called MD&A, management discussion and analysis. So in this part, there's a whole wealth of textual related data on how to decipher the numbers inside these reports, right? And then we also have financial news. For example, Wall Street Journal, Financial Times, just to name a few, right? So these financial news also are largely textual. We then have analyst reports, which accompany their forecasts with a lot of textual data, and social media, which is largely, short sentences written by, these social media users. So given we have so much textual data, we have to think about how to use it, right? So the tools that we have when we first learned, the econometric techniques or machine learning techniques, we know that we need numerical data, not textual data, right? So we have to find a way to translate the textual data or unstructured data into the numeric data. So that's sort of the information extraction part. So to give an example, I took an excerpt from Microsoft's fiscal year 2023 annual report. Okay, so this whole paragraph is talking about the investment that Microsoft is trying to make on this on AI related efforts, right? So they're talking about cloud services. They're talking about having to purchase, have land and energy, and they need to set up the GPUs for their servers, right? So you can see this paragraph actually contains a lot of information, but actually none of this information is presented in a numerical format. So the researchers have thought about how to use this textual information even before the AI became super powerful and super pervasive. So the first attempt that people had made, right? This is actually not too long ago, roughly 15, 20 years ago. People already started to think about how to use these textual information. And the first method people use is this bag of words method. Bag of words method is very simple. It's just basically word counting, right? So you try to gather the frequency of each of the words, and then you use a dictionary to extract, for example, positive words or negative words, right? You just do the simple subtraction of subtracting negative words from positive words and then scale it somehow to get a sentiment score, right? So a very classic paper from this literature is from Logren McDonald, 2021. It's published on Journal of Finance, and they publish a dictionary of different categories of words. For example, positive words, negative words, uncertain words, litigious words, so on and so forth, right? So using this word list, basically you can take the report, then you can cross-reference it in this dictionary and say if I have more positive words than negative words, it's more likely this paragraph is conveying some positive sentiment rather than negative sentiment. So this is just an example how we can do it, right? So we just extract the frequency. For example, data center has appeared twice in the previous paragraph. Manufacturer appeared once, device three, so on and so forth. None of this word is very sentimental, but this is just a part of this part of the frequency of the word that we can see from the previous paragraphs. And then, of course, you can improve upon it. There are several different ways to do the scaling. The simplest way is just to scale the positive words minus negative words by the total number of words. But people say, oh, some of the words may appear more frequently than the others. So maybe we should downweight those frequent words and upweight those less frequent words, right? So those are just minor improvements on our existing methodology. So from this set of research, we already have a bunch of papers that are well published. So here I'm just citing a few, and I'm not going to go deeper into this list. So you can refer to these papers by yourselves. It already helps measure all sorts of all different dimensions of like corporate disclosures. So what else can we do, right? So besides sentiment, besides, like positive or negative outcomes, what else can we measure using this bag of words methodology? Actually, the other thing we can measure is this textual similarity, right? So you can take two pieces of text and you can say, okay, I have maybe a report from 2023 from Microsoft, and I have another report from 2023 from Google, right? Can we compare how similar these two paragraphs are, right? So here we can actually use this textual similarity comparison, also using bag of words. Basically what we do is we form these kind of word vectors, right? So we can basically tabulate the frequency of words for Microsoft, and then we can tabulate the word frequency for Google. And then we can compute what is called a cosine similarity. So this is just one metric to see how similar two pieces of text are, right? And the way to compute this cosine similarity is very, very simple. Basically, you just need to multiply the word frequency from one document with the same word frequency in the other document, just to give you an example, right? So I can just multiply the data center's frequency from Microsoft with data center frequency from Google. And then I sum it up across all of the words, and then I scale it by the norms. Basically, this is a measure of the length of these two documents. Okay, that's it. So that is what's called a cosine similarity. So this similarity is a score between 0 and 1. The closer it is to 1, it means that the more similar these two documents are, purely from the word frequency angle, right? It doesn't care about word ordering, so on and so forth. It just cares about the frequency of appearance. So if it's closer to 0, it means that these two documents are not so similar. Okay, so based on this methodology, Jerry Holberg and Gordon Phillips came up with a whole bunch of papers that are published in all various, a set of very, very good journals. Because you can think about the competitive landscapes across different firms, right? So if Google and Microsoft have very similar product offerings, it means that Google and Microsoft are strong competitors. They're very close competitors with each other, right? If you find a firm whose product offering is very dissimilar to all the other firms, that means this firm is positioned in a place with relatively few competitors, and maybe it can garner higher profit margins, right? So basically, as you can see, using the bag of words, you can already do a lot of things without having to resort more sophisticated AI. So this is just an example of demonstrating the textual similarity. As I mentioned, for example, here I have two sentences: the cat sat on the mat, the dog sat on the log. We want to compare the similarity of these two sentences. So basically, we basically have all of the words listed here, and then we have the frequency tabulated into vector forms, and then I just multiply column by column. So for cat, it would be 1 multiplied by 0. For set, it's 1 by 1, so on and so forth. We sum it up and then scale it. We find that the similarity is 0.6. Okay, very simple calculation. These are some of the references from the Holberg-Phillips papers, and also there's a paper by Paul Tetlock, which also used very similar literature to see whether we have a really, whether the news is still basically regurgitating what's being said earlier, or is this something, or does the news story bring some new information? Okay. So next, I'm going to talk about word embedding. So word embedding takes into the consideration that words are oftentimes, they have nuanced and multifaceted meanings. So simple dictionary-based methods tend to extract information in just one dimension in a binary way, right? So remember that when we think about the Logram-Macdonald dictionary, basically you're just extracting whether this word is a positive word or a negative word. So it's binary, right? Or of course, it can be neither positive nor negative. But basically, it kind of, you can be one way or the other, right? But let me give you a few examples that, the words may be a little bit more nuanced. For example, a word can be neither positive nor negative. And also, for example, good, you have the word good, right? And sometimes we say, this is fabulous, right? Compare good and fabulous, both have positive meanings, but fabulous is conveying some information that is more positive than good, right? If your advisor told you you did fabulous work, you are very happy, right? If your advisor told you you did good work, you might be happy, but you're not that happy, right? This is some kind of, this is sort of the nuanced meaning that the dictionary approach may not fully capture. And the other example is king and queen, right? King and queen are similar to some extent because both belong to the royal family. Both are very powerful. But on the other hand, they're also a little bit different, right? King is usually referring to a male ruler. Queen is either referring to the wife of the king, or is referring to a female ruler, right? So these words are somewhat related, but there are also some differences, right? So the question is, can we find a way to represent the relationship between these words, considering that these words have multifaceted and potentially nuanced meaning, right? So very nice way that were developed, and I will talk a little bit later on the history of this. Is basically there's this word embedding method, okay? So word embedding method basically represents each of the words into a vector, okay, a multidimensional vector. So because it is a multidimensional vector, it has the potential of giving the word very multifaceted and high dimensional meanings. So there's several common algorithms, including fast text, word to vec, Glovi, so on and so forth. And today's discussion, I'm mostly going to focus on the word to vec methodology. So what is the intuition, right? How do we know two words are similar to each other? We know that two words are often are going to be similar to each other if they often appear in similar contexts, right? For example, coffee and tea. I just had a cup of coffee in the morning, right? But if you're a tea lover, maybe you don't want to drink a cup of coffee in the morning, but rather you would take a cup of tea, right? So we know that coffee and tea are similar things. They're drinks that are refreshing, right? That can help you keep you awake. So how do we know that these two words are somewhat similar, right? We can basically learn from the corpus, from our training data, that these two words oftentimes appear in similar context, right? I need a cup of coffee to start my morning. She prefers a cup of tea with her breakfast, right? You can see this coffee and tea appear in the context of cup, right? Cup is basically the container for coffee and tea. And also sometimes we see drink coffee, drink tea, right? So if we can see these kind of coffee and tea appear in similar contexts, we will know that these two words are somewhat similar. So how do we get to this idea? So there are two words to train this model, the word-to-vec model. One is called continuous bag of words, or CBOW. Basically, the continuous bag of words is trying to represent the center word using the surrounding words. There's another way to train this model. It's called skipgram. Skipgram basically masks the surrounding words, and you basically use the center words trying to predict the surrounding words. So I'm going to mostly introduce the CBOW, the continuous bag of words methodology, but the idea is basically similar. So let me just show you some of the examples. So just take this earlier paragraph, for example, right? So the earlier paragraph that I took from Microsoft's report. So one of the sentences contain investment making cloud, AI infrastructure, devices, continue increases, so on and so forth. Okay. So basically what we will do is to start, for example, start from a 5-word window. Okay. So we basically in the first attempt, we're going to mask investments. So investment is something that the program doesn't see. It only sees the surrounding words like making and cloud, and it's going to try to use making and cloud to predict what is that masked word. Okay, so it's going to try to predict this word investment. Okay, and of course, we can move this window one word at a time. So next in the next iteration, we'll have investment making cloud AI, so on and so forth. And then the center word is the second word, which is making. So in that case, we're going to use the surrounding words to predict the center masked word, which is making. Okay, so on and so forth. So we're going to shift this window one word at a time. And each time we have the center word being masked, and the program or the algorithm will try to predict the center word, right? So that's basically how this model, this continuous bag of words, is being trained. Okay, what is nice about this way of training this is because, remember, all we need for this kind of training, we don't need a lot of human labeled data. We don't need to hire 1,000 RAs to help us to say which words should appear with other words, right? All we need is to take this corpus from the internet. For example, Wikipedia 10Ks, right? So in these data, we already have a lot of information. About which words appears with the other words, right? So it's very easy for us to acquire these training data. So that makes our training quite straightforward. So this is how we train this. So this is sort of the network structure of the specific training. As you can see, we're going to use the 4 surrounding words and trying to predict the center word. Okay, if it does a good job to predict the center word, then the error will be relatively low. On the other hand, if the prediction is far from the actual center word, the algorithm will try to update itself so that the parameters will be revised to achieve better fitting of the data. Okay. So a few technical detail, again, if you're just going to use this methodology, maybe this is not so important. So each of this word here is represented by one hot encoding. So it's just a fancy way to say that, if I have 3,000 words in my dictionary, I'm just going to have a vector of 3,000, right? So if the word investment appears, then I'm going to encode that word investment using this 3,000 element vector, where only one element is 1, which that element corresponds to the word of investment, whereas all the other elements will appear as 0. Okay, that's what we call one hot encoding. So the second layer here, the embedding layer, is where we sort of try to represent each of the word. Okay, so after the model is being trained, we are able to extract the embedding layer, which is marked in yellow on my chart. So you can see here the embedding layer is just 5 different elements. We are using a 5-dimension vector to represent to represent each of the words. But in practice, this embedding layer tend to be quite large, right? Sometimes 150 elements, sometimes 300 elements, depending on the specific corpus that you're using. So the output here, the one that's marked with a green circle, essentially will tell you the probability of the center word, right? So it's going to say what's the likelihood that the center word is investment, what is the likelihood that the center word is cloud, right? If the likelihood is for investment is very high and your actual center word is investment, then this model will receive a very high score. On the other hand, if the match is very bad, then this model will receive a low score, and then you're going to tell the training algorithm to do further training to adjust the parameters so that the model will perform better in the next iteration. Okay. Um, so let's talk about how to use embedding, right? So I mentioned that embedding is better to a large extent is better than the pure dictionary method because it can represent this high dimensional meaning. So let me give you a few examples. Okay. So one thing we could do is we can calculate the cosine similarity between two words. The previous example I gave you, saying that king and queen are somewhat similar, we can actually measure how similar they are using the embedding vector representing the queen and the embedding vector representing the king using the cosine similarity measure, right? Using the cosine similarity measure. And what else you can do is that, say, if you want to measure a specific concept, right? If you want to measure corporate culture, then you can start from a few words related to corporate culture, and then you can use the embedding to find similar words to these seeding words, right? So you can expand your dictionary to a longer list. So that way you can make your dictionary potentially a lot richer. So this is one way to use the cosine similarity using of embedding. The other is that you can actually find this really interesting relationship between words, right? So queen, as I mentioned, queen and king are somewhat similar, right? So using this embedding vector, you are able to find this interesting relationship that queen is roughly speaking a king minus a man plus a woman, right? We know that, like queen and king are the main difference between queen and king are their gender, right? We know that we can also represent Paris roughly using Tokyo minus Japan plus France, right? Why is that? Think about it. Tokyo is the capital city of Japan, right? So we say Tokyo minus Japan, so it's not Japan's capital, but it's France's capital. So France's capital is Paris, right? So we can do these kind of interesting representation, we can find this interesting relationship between different pairs of words. But keep in mind that this relationship is very much dependent on what kind of data you use in training, right? So if your training data contains a lot of this information about different cities, then you're able to find this very rich representation of the relationship between different cities, so on and so forth. What else can we do, right? One thing we could do is we can remember previously we mentioned the textual similarity using bag of words approach, right? But maybe you can do a little bit better. You can represent the text using this word embedding, right? You can have the word embedding of all the words in a paragraph. You can add these embedding you can average these embedding, and then you can compute the embedding based textual similarity between one document and the other, right? So this will just give you a little bit better representation of the text. But actually, you can do even better than that. There's a very related method called doc2vec. So doc2vec is just representing the whole paragraphs instead of looking just at the word embedding. So, and there's also a Holberg-Phillips paper that used doc embedding recently, and I think it's probably forthcoming at the Journal of Finance. Okay, so I also gave you a link here. So if you want to play around with this kind of word embedding, there is a pre-trained word embedding model which is linked on this page I'm giving here. You can feel free to play yourself. Okay. This is the vector. So I made a very rough graph of the representation of Paris, Tokyo, and Japan, France. So you can see sort of this representation on the space of the this is purely for demonstration purposes. It's really not, it's not really taken from the training data. Okay, so if you want to see what the training data look like, you can go to the website that I gave you earlier. What kind of research have been done using the word embedding, right? So one of the paper is by Andrew Wu from the University of Michigan. He's both in the finance as well as in the operations department. He came up with this supply chain based method that used the embedding to come up with to find what is the supply chain risk based on the embedding model trained on the conference calls. And the other is the paper by Kylie and her co-authors. So basically, they created this corporate culture dictionary based on word embedding. And I mentioned Holberg and Phillips has had this Doc2Vec paper, and there's a lot more. And if you're interested, these are the papers that you can take a look before thinking about your own research. So let me maybe take a pause here because this is sort of the old stuff. This is kind of the stuff before the large language models, the transformers became very important.